Okay, so let's conclude our discussion related to sequential circuit design. And if you recall that in the last lecture, we were seeing how one can design a sequential circuit. And we said that we can model the sequential circuit in terms of a Mealy state machine, and where we think of a sequential system as consisting of a number of states. And depending on the nature of the input, the system goes from one state to the next and produces a certain output. And this is captured in the form of a state transition graph. And so starting from the behavior of the system, we try to capture it in the form of a state transition graph. And then we implement the state transition graph in terms of this block diagram here, which consists of two combinational logic circuits. One is a next state logic, which makes the memory element go to an appropriate state with the clock cycle. And then there is an output logic which generates the proper output depending on the input and the present state of the system. So the design of the finite state machine. So we have finite number of states and the system goes from one state to the next. So we call it a finite state machine, FSM. So the design begins with determining the number of storage elements based on the number of states that are there here. In general, we try to use as few storage elements as possible. And once we choose a storage element, then these are symbolic states. So we assign bit values to these symbolic states here. And then we decide how we are going to implement the storage element, how we're going to implement the memory, choose a D flip-flop or a JK flip-flop or a toggle or a T flip-flop. And once we have done that, then we generate the state transition table and we use that to synthesize the next state logic and synthesize the output logic here. And then that completes the design of the sequential circuit. So let's look at a specific kind of a sequential circuit, which we call as counter. And so the counter is a sequential circuit. We are talking about circuits so far which are synchronous. So everything is driven by a clock. And so the counter goes through a series of states here. And goes through a series of states and cycles through them. So it starts from state S0 to goes to S1, S2, S3, S4, S5, S6, S7 and comes back here. So there are different counts of counters. This is and the values of the states are specified here. So S0 is 000, 001, 010, 011. So we call this as a binary up counter. So it starts from a binary value 0, then goes to 1 and 2 and 3 and 4, 5, 6, 7, and then comes back here. And we also call it a modulo 8 counter here because the whole thing repeats after 8 clock cycles here. If something repeats after 5 clock cycles, we will call it a modulo 5 counter, and so on and so forth here. So counter then goes through a fixed series of states and cycles through them, right? And so we need to then, so in this case, the output of the sequential circuit is basically the states themselves are the output. The values of the memory elements in each one of these states is the output here. So how can we design it? So since there are 8 states here, we are going through 8 states, so we require 3 flip-flops. And we can choose different flip-flops. So we had seen how to design using a D flip-flop and a JK flip-flop. So in present case, let's choose a toggle flip-flop, T flip-flop here. Right, so our entire circuit then becomes, since we have 8 states, we are using 3 flip-flops here, toggle flip-flops here. Their output is ABC, QA, QB, QBC. And there is no explicit output. The outputs themselves are the outputs of the flip-flops, as we said. And so we have to synthesize this next state logic here. So the purpose of the next state logic is to produce appropriate values here, inputs for the toggle flip-flops, so that they go to the appropriate next state there, right? So we generate the state transition table. So the present state, let's say 000, and then the next state, there is no input here. So the next state is 001. Next state is 001. And so for a flip-flop A to go from 0 to 0, well, the toggle input can be 0, because if you make the toggle input 1, then the flip-flop will toggle. It will go from, if it is 0, it will go to 1. If it is 1, it will go to 0 here. So flip-flop B goes from 0 to 0, so we keep TB equal to 0. Flip-flop C goes from 0 to 1, so we keep TC equal to 1. Then if the system is in 001 state, then the next state is 010, and we determine appropriate values of TA, TB, TC here. And like that we fill up the table here. And then we find out expressions for TA in terms of the present state values. Expression of TA in terms of present state, meaning QA, QB, and QC here. So that we can do. TA equal to B dot C. B is referring nothing but to the output of the B flip-flop here. So this we know how to get a minimized Boolean expression. So TA equal to B dot C, B ANDed with C, TB equal to C, and TC equal to 1. Right, so we can do that, and then that completes our design there. So we can now replace this next state logic with this value here. Right, so we can do that here. TA equal to B dot C, TB equal to C, and TC equal to C here. So we simply put 1 here, TB equal to C here. So output here of the C flip-flop is fed here, and TA equal to B dot C here. So B is fed here, and C is taken from here and ANDed and fed here. And so this becomes a binary up counter. So if we switch this particular circuit on, and as the clock comes, the system will go through 000 to 001 and up to 7 here, 111 here, and then back again, and it will keep going until the clock is available and until the circuit is powered up. So we can take our counter, and we can add an enable pin also. We have seen in previous lectures that an enable pin can be a very useful feature. You can, using that particular pin, you can at any time you can disable or enable your piece of circuit. And so enable can be done by simply so adding an enable pin, enable input here through an AND gate here. So earlier this one was fed directly to T, but now we feed it through an AND gate here. So note that when enable equal to 0, the input here T equal to 0, and therefore nothing happens to the output. The system stays in its present state here. So the counter doesn't count. And similarly, enable pin is 0 here, so TB becomes 0 here, enable pin equal to 0 here, TA equal to 0 here. And therefore the whole system then stays in its present state. The moment you make enable equal to 1, then of course all these, the values that we had determined earlier, the TC equal to 1 and TB equal to, basically equal to, TB equal to basically equal to C value here, and TA will be equal to B dot C here. So all that then are enabled, and then the counter starts working here. All right, so easy to add an enable pin there. Okay, so that's counter is in hold state. It maintains whatever state it is in. With the enable equal to 0, it remains in that particular state there. When enable equal to 1, the counter begins to count. We can also add, sometimes this is also a useful feature, we can add an asynchronous reset here. And asynchronous, so it doesn't depend on the clock. And reset means it will set all the flip-flops, all the outputs to 000 here. And note that this is active low. Whenever we put a bubble here, it means that if you put this pin, this input as 0, then the system will reset to 000 here. And so this is done by putting a reset input to each one of those flip-flops and connecting them up and defining a overall reset terminal here. Right, so that's also something that can be done easily, provided we have a T flip-flop with a asynchronous reset input here. All right, so this is a example of another counter which counts from 000, so it's binary up counter up to so 000 to 1 to 2 and up to 15, and then back again here. So it's a modulo 16 counter here. It repeats after 16 cycles. And so we could use the procedure that we had used earlier to design, but in these simple cases sometimes a formal procedure is not necessary. We can actually examine the behavior here and sort of determine what the logic is in order to cause these kinds of transitions here. So for example, we note that T is toggling with every clock cycle, A clock cycle comes, D goes from 0 to 1. Another clock cycle comes, it goes to 0, and then 1, and then 0, and then 1, and so on and so forth. So that's the behavior of D, is toggling with every clock cycle. C, on the other hand, note that C toggles only when D is 1. When D is 1, then C goes from 0 to 1. And then D is 0, nothing happens here, it remains 1. Then D is 1, then C again toggles here, right? And so we see that behavior. C toggles only when D is 1. Similarly, if we look at B, B toggles only when both C and D are 1. When both of them are 1, then it goes from 0 to 1 here. Again, both of them are 1, so it toggles. It goes from 1 to 0. And again, both of them are 1, so it goes from 0 to 1. So B toggles only when both C and D are 1. And similarly, A toggles when both B, C, D are 1. When B, C, D are 1, A will toggle, will go from 0 to 1. Again, B, C, D both are 1, and then A toggles again here. So when we see this kind of a behavior, it's easy to implement using T flip-flop, noting that T flip-flop will toggle when T equal to 1. And when T equal to 0, it's in the hold state here. So it's easy to build up a circuit for a 16 state counter, 4-bit binary up counter here. And so D toggles with every clock cycle. So we take this flip-flop here, D here, and we put T equal to 1, right? So it will toggle with every clock cycle. C toggles when D is 1. So C toggles, so if we take this C flip-flop, so whenever D is 1, so we take the output here and we put it in the T input here. So whenever the output of D flip-flop is 1, this flip-flop will toggle. B toggles when both C and D are 1. So we use an AND gate to combine C and D, and B will toggle then only. And finally, A toggles when both B, C, D are 1. So we've already generated CD here, and we combine it with B here. And so A will toggle when this thing here. So we don't need when the transitions are simple, and sometimes when we examine the state transitions, we can come up with these behaviors, and we can directly map it onto the gates that are there here. But otherwise, we have a formal procedure, which we just described earlier, of how to design any counter which goes through any set of states there. All right, so that's BCD here. Well, you can have a 4-bit down counter. So in the previous case, it was an up counter. We were starting from 0 and going all the way up to 15. In this case, we are starting with 15, going to 14, 13, 12, and then 1 and 0, and then back again 15. So a counter always starts from one state, goes through a series of states, and then come back to the same state here. So we want to design a 4-bit down counter. So we see again that D toggles every clock cycle here. And then we see C toggles every time D is 0. And B toggles only when both C and D are 0. So it's a similar behavior, except that in this case, A is toggling. For example, note that A will toggle only when all 3 B, C, D are 0s here. Then A goes from 1 to 0 here. Then again, when all 3 are 0 here, A toggles here. So we can again, in a very similar manner, write these down and then map it onto the 4 flip-flops here. And note that now, because C toggles only when D is 0, so we take the complementary output here. So when D equal to 0, we put it into the T input of the C flip-flop here. And similarly, the other inputs are decided according to this behavior here. All right, so that was so this is an example of a binary, a 3-bit binary down counter starting from 111 to 110, 101, and then 00 here. We can also talk about, so far we've been talking about, so this is a 8 states are there. So we also call it modulo 8 counter here. Well, so this is an example of a decade counter. So it starts from 000, goes up to 8, 100, then 1001, 9, and after 9 it comes back here to 00 here. So we call this a decade counter. It goes from 0 to 9 and then back to 0 here. And we also call it, because it has 10 states, we call it modulo 10 counter here. This is an example of a modulo 5 counter, 000, 001, 010, 011, 100, and back again to the same. So each one of these counters we can design and using the approach that we just talked about. So this is an example of we just discussed the example of a 4-bit up counter where QB is fed and QC and QD are fed. This is an example of a down counter which starts from a 11115 and then counts down. And we have added a pin here, U/D here. So if U equal to 1, up equal to 1, then each one of these connections is enabled. On the other hand, if I put U equal to 0, then the whole connection is disabled. So the counter will not count and it will be in the hold state. In this case, again we have added, but the same input U/D is fed through an inverter here. And note that it is QD bar which is fed here and QC bar which is fed here. So which means that if you make U/D equal to 0, then this one becomes 1. And then the whole, all the inputs are enabled and it becomes a down counter. So you can think of combining these two circuits together such that it can become, depending on the value of U/D here, it can do both. It can count up and as well as count down here. So combine these two counters together such that, so combining means note that TD in both of these cases is 1. TC in one case is fed through this circuit, in another case it is fed through this circuit. So now TC combine the output of this one and combine the output of this one and feed it into TC, into the TC, so that depending on this input here, up or down, the counter will count either in an up manner here from 0 to increasing binary values, or down from let's say 1111 to then to from 15 to 14 to 13 and so on and so forth. Then there is a counter called BCD counter. So BCD counter uses a number representation in what we call as a binary coded decimal, where each decimal digit is coded as a 4-bit binary number. Okay, so for example, if you have a decimal number 25, now 25 we could code it in a simple binary number, but here we are calling as a binary coded decimal. So each digit that you see here is coded in a 4-bit binary number. So 5 is 0101 and 2 is 0010 here. All right, so this is called binary coded decimal. And so when you use this representation, it's very easy to take this kind of a number representation and understand what that particular number in binary represents. Otherwise, there is if we have an 8-bit number or a 16-bit number, it becomes more difficult to immediately see what that particular number is. But when it is in binary coded decimal, you just take each set of 4 bits represents one decimal digit here. So it's a very simple representation and sometimes it's useful here. So so binary coded BCD counter is something that goes, let's consider the following counter, which starts from 000, goes up to 1001, and then back to 00 here, right? So consider a counter like this here. So it's basically a modulo 10 counter. But let's also consider that it produces an output. Every time you reach a 9 here, you produce an output Y, okay? And so that is useful when you want to have a 2-digit, let's say 2 decimal digit counter here. So what you can do is you can take, so we can easily design this counter here and we can easily generate a Y also. So Y will be equal to 1 anytime A is 1, B is 0, C is 0, and D is 1 here, right? So it's easy to generate, put a gate here, put a small combinational logic which will generate Y equal to 1 anytime this pattern is there here, right? So this output Y, and we know how to go from one state to the next and generate this kind of a counter here. We've already seen examples. So BCD counter can be designed, and let's say it has an enable input also. So when we enable this particular input, it will count. It will go from 000 up to 1001. The moment 1001 occurs, it will generate a 1 here. And it generates a 1 here which enables this particular counter, and which enables this particular counter here. So this will count. But then note that immediately in the next clock cycle, it will go to 0 here. Right, so let's see. So this one will be able to do BCD counting. Okay, so let's see how this works here. So we have two BCD counters cascaded in this particular manner here. So initially note that so we enable this, and initially this is 0. So we start from 0 0 0. We'll go to 0 0 1. Note that this is disabled, so it stays in here. We go to, eventually we'll go to 1 0 0 1. We'll reach 9, and still it is 0 0 0 here. Then what happens is the moment it goes 1 0 0 1, this becomes 1 here. Okay, so it produces an output 1. Now next clock cycle comes, this enable pin is enabled here, and so this one now it will start counting. So it will go to 0 0 1 here, and this one goes from 1 0 9, it goes back to 0 0 here. So it goes to 0 0 here. The moment that happens here, this again becomes 0 here. So again it is disabled. So note that after 9, and each counter represents a decimal digit here. So from 0 to 9, and then when we go to this particular clock cycle here, this is 0 and this is 1. So we've gone to 10, and then it goes to 1 here. So we've gone to 11, and eventually we go to 19, 1, and this is 9 here. So the moment this goes again, this will become 1, and this will on the next clock cycle goes to 0 0 1 0. So it goes to 20. So like that we can count from 0 to 99 here. So our counter will go from 0 all the way to 99, and then back to 0 here. So we can count from 0 to 99. So it's a BCD counter counting from 0 to 99 there. And each one of these counters we can design using the approach that we just talked about here. Now when you have, sometimes you're using let's say 3 flip-flops, and the number of states that you're using are less than the number of states that 3 flip-flops can have. For example, if you're using 3 flip-flops, total number of states are 8. But let's say your counter only uses 1, 2, 3, 4, 5, 6 here, right? It only uses 6 states here. And so when you're using 6 states here, then 2 other states are not being used, 0, 1, 1 and 1, 1, 1. So the issue is, what do we do with that? Right? So one approach to handle this situation is that, when you are in 0, 1, 1 and 1, 1, 1, we can take that the next state could be anything. So we use don't care conditions corresponding to these unused states here. So suppose the system goes 0, 1, 1 here, the next state could be anything. Okay, so and that would help us to simplify our flip-flop inputs and result in simpler logic there. So for example, this is there here, and so for example 1, 1, 0 was an unused state, and so we put X here, and 1, 1, 1 was an unused 0, 1, 1 was an unused state, and 1, 1, 1 was an unused state, so we put a don't care state here, and we use that to simplify. Right, so that could be one approach. But when a counter goes through a less number of states than the maximum number of states that is possible, there is a possible problem that can occur is that suppose by chance a counter gets into one of those states which is not specified here, so into one of those unused states. Now if it happens to go there, then it's important that the counter recovers. The counter recovers, so let's illustrate that. So let's say this is a counter that we have just designed. So this counter is going from 0, 0, 0 to 0, 0, 1 and 0, 1, 0, 1, 0, 0, 1, 1, 0 and 0, 0. And there are 2 unused states, 1, 1, 1 and 1, 1, 1 here. Okay, and so if by chance the system does go into this particular 1, 1, 1 states. Now if you're wondering how, let's say we switch on the system, and when we switch on the system, suppose conditions at that particular time prevail in such a way that all 3 outputs, they go to 1 here. All right, So we'll not get into the details of how the system goes, but suppose it does happen to go to 1-1 state here. Then we have to make sure that if it does go here, it comes back to this particular one of these states so that it recovers, and then this counter begins to count in this particular fashion here. Right? So let's say it goes into 1-1-1 state here. So if it goes into 1-1 state here, then we can, according to the logic that we have here, note that this is 1 here, so this is 1-1, and this is again fed here, 1-1 here. So we can see that in the next clock cycle, it will go to, according to the inputs that are there at JK here, in the next clock cycle, it will go to 0, 0, 0 here, right? So it comes here. And once it comes here, then we know our counter will go to 0, 0, 1 and 0, 1, 0, and so it's back into its normal position here. So that's a nice feature, that anytime a counter goes into, by any chance, into one of those unused states, it should recover and come back to the used states which are actually used there. Similarly, 0, 1, 1, you can check that if the system does go to 0, 1, 1, which means A is 0, B is 1, and C is 1 here, you can check that the system will recover to 1, 0, 0 state here on the next clock cycle. Okay. The counter that we have been talking about, it can be looked upon as a frequency divider. Note that the clock that is coming in is at a certain frequency. And if we look at the state of the counter starts from 0, 0, 0, and then it repeats after 8 clock cycles here. So it's sort of, the whole pattern that we have repeats after 8 clock cycles. So it's like a divide by 8 counter. So let's see here. So suppose we have a clock like this here. And if we look at the input C here, so C, so C is initially 0. 1 clock edge comes, so it toggles here. Another clock edge comes here, then it toggles again here. Then it waits for the next clock edge, so it toggles here. Then waits for the next clock edge, toggles here. And like that, C goes here. So you can immediately see that the period of C is twice the period of the clock here. So it says the output C has a frequency which is half the clock frequency. Similarly, we can plot the output B here. The output B that you can see here, so it's a divide by 4. It divides the frequency by 4. And then you can see here, it divides the frequency by 8 here. So if you look at A, it divides the frequency by 8 there. And so counters can be looked upon as frequency dividers. So that's something, if in different places in the circuit you require a signal with different frequencies, you can use counter to carry out the division. Division by 2, division by 4, division by 8 here. So F by 2, F by 4, and F by 8 here. Suppose from a frequency of 10 kilohertz, you are required to generate a signal of frequency 1 kilohertz. All right, so you want divide by 10, basically. So you have, so note that this is the clock, and you would like to generate an output which is shown over here, right? So for 5 clock cycles, it is low, and for another 5 clock cycles, it is high. So you want to divide by 10. You want to divide the frequency by 10 here. So if we use a decade counter, 0, 0, 0 to 0, 0, 1 to 1, 0, 0, 1 here, and then we note that the whole pattern repeats after 10 clock cycles. But if we look at any of these outputs, the outputs don't resemble this kind here. So for example, if we look at A is, note that A is 0 here, 1 clock cycle, 2, 3, 4, 5, 6, 7, 8 clock cycles is low, and 2 clock cycles is high, right? So it produces, it doesn't produce the right output here, okay? It doesn't produce the output that we are looking for, 0, 0, 0, 0, 1, 1, 1. So we don't see that anywhere in this decade counter here. So what we could do is, we could note that, so this is the behavior here, right? For example, if we have 0, 0, 0, so this is a divide by 5 counter. So we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and 1, 0, 0. So this is what happens with A. A goes like this here, right? So it's a divide by 5 counter. And so the idea here is that we are looking for this kind of a behavior. And so the idea is that you use a divide by 5 counter and then further divide it by 2. Okay, so let's see here. So we have a modulo 5 counter, which is a divide by 5 counter, modulo 5. So modulo 5 counter, we just said, will work like this here. After 4 clock cycles, it goes 1 and then returns back to 0 here, right? So it will go like this here. And then we follow it up with a divide by 2 counter. So a simple toggle flip-flop is a divide by 2. So we feed in the A here, this part here, we feed in into the toggle flip-flop. And so now what will happen is, note that A is 0 throughout here. So output Z is 0 here. Now this goes 1 here. Okay, so still the toggle flip-flop just before the clock edge was 0, so it will still stay 0 here. Now the T input is 1 here, so it will toggle. So output will go 1 here. But then after that, this goes to 0 here, so it will stay 1 for the next set of clock cycles when again this goes 1 here. So now we'll be able to generate the signal that we wanted was. We wanted a divide by 10. So for 5 clock cycles, it is low. For another 5 clock cycles, it is high. So instead of using a direct decade counter, which didn't give us the output signal of the kind that we wanted, we used a modulo 5 counter here. And then used that modulo 5 counter, cascaded it with a simple divide by 2. And that gives us the required pattern here. Alternatively, what you could do is you could design a divide by 10 counter with the following states here. All right, so a different kind of a decade counter or a divide by 10 counter where you start from 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, and then you go to 1, 0, 0, right? 1, 0. So the moment you go to 1, 0, 0, we keep this bit 1. So it goes to next state here, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1. So it's not a simple binary up counter up to 9, but we design this counter so that it produces the output like this here. So it's 0 here, the bit A is 0 here. B, C, D are going in the same fashion here. And then A goes up after this one here. And then this part again goes from 0, 0 to 0, 0, 1. And so if we design it like this, then it will produce an output in this particular manner here. Okay, so another example from a frequency of 10 kilohertz, generate the following signal of frequency 2 kilohertz here. All right, so this is a note that is a divide by 5 counter here, but it is going in this particular manner here. Is 0 for 2 clock periods and then 1 for 1 clock period here. So a divide by 5 counter has these 5 states. A simple divide by 5 counter 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and 1, 0, 0, right? And so we modify it. This divide by 5 counter will not give us this particular pattern. So we modify, we can decide which state follows which state here. So we have 0, 0, 0, 0, 0, 1. So we are focusing on bit A. So it is 0 for 1. And then in the next state, we convert it into 1. And we keep it 1 for 3 clock cycles here. And these ones we adjust. 1, 0, 1, 1, and 0, 0 we adjust so that they are distinct states here. So now we know that if a counter goes through these states, then we will generate an output in this particular manner here. And then we can, design the appropriate circuit where the system goes through these particular states there. So any kind of a waveform that you see here, you could map it onto a particular set of states. And as the system goes through those particular states, you will get those particular waveform there. Okay. All right. So there's a specific counter called ring counter. So ring counter is like one only, for example, this is a ring counter with 4 flip-flops. And only one of the bits is 1. One of the output is 1. And with clock cycle, that output 1, it circulates. It goes in a ring. So starts when T0 is 1, then T1 becomes 1. Then T2 becomes 1 and T3 becomes 1 and then back again. Okay, so this 1 is sort of circulates in a form of a ring. once there's a single one and it circulates in that particular circuit there. And there are different ways of designing it. We could, for example, one way of doing it is we could do a 2-bit counter, so which goes through 00011011. Note that our system has only 4 states, so a 2-bit counter goes through this. And then if we feed it into a 2:4 decoder and realize what a decoder is, so when you have 00 in the decoder, only one of the input is high and all others are low. So when 0000 is there, then only one of them, only one bit will be high, and therefore this will give us a ring counter here, a normal 2-bit binary counters followed by 2:4 decoder. All right, so there are several other kinds of counters that are there here. This is an example of a counter which we call as a ripple counter. And it's an example of asynchronous counter in the sense that all the flip-flops are not driven by the same clock. And so if you notice, it's made up of T flip-flops, and the output of the first flip-flop is fed into the clock input of the next. Then the output of this one is fed into the clock input here, and the output of this one is fed into the clock. And these are negative edge triggered clock. And keep in mind that T flip-flop will toggle when T equal to 1, otherwise it is in the hold state. So clock is negative edge triggered. So let's see how it works. So initially, let's say it's all in 000. So and the count, we give a pulse here. We give a pulse here, so this one will go from 0 to 1, right? 0 to 1, and note that there is no clock. There's no clock edge, negative clock edge to any of the flip-flops here. So they stay in 000 here. Well, then this again goes into, we give a pulse here. So now this will toggle. It will go from 1 to 0. And as it goes from 1 to 0, it creates a negative clock edge for this one, right? So this will go from 0 to 1. And the others will stay 0, 0. This one then will go to 0 to 1, and as it goes from 0 to 1, it creates a positive clock edge, but it doesn't do anything here. So it stays 1, 1, 0, 0. Then it will go again 1 to 0, and as it goes from 1 to 0, it will trigger this particular flip-flop here. So this one will go from 1 to 0, and as it goes from 1 to 0, then it will trigger this one. So it will go from 0 to 1 and then go here. And like that, you can see here, so the, so a change here ripples through to a change here, which causes a change here, which can ripple into clock input of this particular flip-flop and cause a change here, right? So that's why we call it a ripple counter here. And you can see it's counting from 0, 1, 2, 3, 4, 5, and eventually 15. Now, once it is 15, when all of them are 1, again, a clock comes here, and this will go 1 to 0, right? It will go from 1 to 0, which will then trigger this particular flip-flop. So this will go to 1 to 0, which will then act as a clock for this one. This will go to from 1 to 0, which will act as a clock for this one. This will go from 1 to 0 here, right? So they will act like this here. So it will go to 0, 0, and then the whole thing repeats here, right? So this is a ripple counter which counts from 0 to 15. Note that the interesting thing about this particular counter is the simplicity. We are not using any gates or anything at any of the inputs here. So it's, all you require is flip-flop and some interconnections, and you're able to count from 0 to 15. If instead of feeding A0 to the clock input, if you feed the A0 bar here, you can verify that this acts as a ripple down counter here. So I'll skip that. Ripple down counter here. So there are many other counters. For example, there's a BCD ripple counter and so on and so forth. But let's stop here, and then this is the second last lecture. In the next lecture, we'll summarize the course.